Let's talk about why is it difficult to run low latency, high concurrency workloads on a data lake, right? So what is the problem that needs to be solved? So the main difference between a data warehouse, a proprietary shared nothing data warehouse, when compared to a data lake, right? Creating a data lake is mainly the process of fetching data and metadata, right? And this part can be easily become the bottleneck of your whole query path, right? So first, you have to consider the I/O, the network I/O, right? After all, you're fetching data from external storage. It needs to use a lot of network I/O, right? Not only itself is very slow, it can actually slow the query execution process as well, because any ad hoc engine that's designed to run joins and high cardinality aggregation, it does a shuffling service. It has a shuffle service or data shuffling during the query execution, which means that data are transferred are reshuffled between your nodes, during the query process, and this needs network IO as well, right? And so this fetching process not only is slow itself, it can you know um, make your execution slow as well, right? And also you have to consider the slow performance of data lake storage device. The storage device that data lake system usually run on, like HDFS, is on-prem or in a Hadoop environment, or cloud object storage, for example, like AWS S3, right? The latency of AWS S3 can be north of 100 milliseconds, which is quite slow when it compares to a local NVMe drive, right? And also data files can be unoptimized for query performance, like we just talked about, right? If your data is not compacted correctly, scanning the data files can be expensive and slow, right? So this is the main cost of running really fast data lake queries. And let's take a step back and look at the bigger picture, right? Data Lakehouse, the table format has received a lot of updates. We have not only limited to Apache Iceberg, but a lot more, a lot of other innovations as well, right? Like Apache Hudi and Delta Lake and Python, right? But people are still using query engine that were not really designed for data warehouse use cases. High concurrency, low latency use cases. Some of them are, instead of they're optimized for performance, but they're optimized for long running batch workloads, right? More for stability, not for low latency, high concurrency. Or they're built for another architecture like data mesh, right? They're built to connect into different data sources instead of purely maximizing performance, right? It's probably written in a higher level language for faster development instead of using a lower level language to squeeze out every ounce of performance, right? So this is a problem we see. So how does StarRocks accelerate data lake query? This one slide can be a webinar by itself, but to highlight, there are three things that are absolutely crucial. So first is that StarRocks has a data and metadata caching framework that's based on both memory and disk to solve the problem, the data fetching problem just talked about, right? So first, it overcomes the slow performance of data lake house storage, right? Like HDFS or cloud object storage. And it also saves the IO cost from fetching the data from external storage devices, right? And also StarRocks has an MPP architecture that features in-memory data shuffling. Not only the data shuffling part, the entire query process of StarRocks can be done purely in memory, right? So this way, StarRocks is really optimized for low latency, high concurrency workload instead of batch workloads, right? And also, StarRocks is the execution layer is completely written in C++. So it's really so StarRocks can take full advantage of the CMD instruction sets, right? Plus the vectorized execution engine. So to process everything in batch, process everything in columnar in batch is really good. It's really crucial, to getting the fastest performance, on OLAP queries, because OLAP is everything's in column, everything's in batch, right? With the right optimizations, getting data warehouse like performance on a data lake house is actually quite easy. And I'll show you some numbers just right here, right? StarRocks, I mentioned earlier, works as a data warehouse and it works as a query engine on the open data lake, right? So as a data warehouse, data is stored, remotely in the cloud object storage, but in Star's own format, right? And CN, the compute nodes, cache the data locally, but in a Star's table format, right, as well. But when Star's is on the open data lake, it queries, open and standardized file formats managed by open table formats such as Apache Iceberg, right? Let's see the difference between the two. So first, StarRocks is really fast as a data warehouse. When compared to other real-time data warehouses, StarRocks is ahead, right? So this is the SSB benchmark test. So everything with a flat, you see on the right-hand side here, everything with a flat is a variant of this SSB benchmark test created by Lakehouse, right? So basically, SSB originally is multi-table, right? So this flat is a denormalized version of that that multi-table test. So basically pre-drawing everything into a big flat table, and then only do on-the-fly aggregation instead of doing on-the-fly join, right? And the multi-table is the original test that's with the join operation, right? And you can see here, actually, StarRocks is faster than the two, than both ClickHouse and Apache Druid on the flat table schema, where the only on the fly aggregation, no join. But StarRocks with the join is even faster than Druid's flat table performance and is almost as fast as ClickHouse flat table performance. This is kind of remarkable because join is probably the most expensive thing you can write with a SQL, right? So this slide basically showcases how fast StarRocks is as a data warehouse. And here, let's compare the two solutions, StarRocks as a data warehouse versus StarRocks as a Lakehouse query engine. So data warehouse, actually, to get the maximum performance for the warehouse, this is using the share nothing mode. So data is actually persisted in the local NVMe disk. So maximize the performance, right? Hot queries, same exact hardware on the TPCDS 1 terabyte benchmark test. The data warehouse solution is only 12% faster than the data lakehouse solution on top of Apache Iceberg. So this means a lot because by giving up 12% of the performance, you're getting what? You have the chance to unify all of the workloads on one single copy of data in open and standardized format, which is easier for governance, is cheaper, right? You gain all of the data lakehouse promises by just giving up 12% of the performance, right? And that's massive amount of gain.